Hey y'all, what's up? My name is Cram, and I'm out here making this game called Konanima, which is this music-based JRPG where you go around and you explore the world and learn concepts about music theory and literature and all of that good jazz. Now, in a JRPG, we often have multiple members within a squad. You can see that this is the current person who is the leader because everyone's following this person right here in the front. Now, if I wanted to, I can actually change who the leader is and everyone else follows that new person instead. We can do that by holding tab. This animation pops out and you can kind of see that we have the options to pick between any of the different people. The current leader is marked with this crown above them. But let's say we wanted to pick Isla. She is currently denoted here. If we hit D, Isla becomes the new leader, and now everyone starts to follow Isla. When I was working on this animation, I thought it looked really clean at first, but then I was playing this game called Omori, and I saw their animation, and it just looks, I think, so much cooler. It's also a JRPG, by the way, so they also have like a squad system where there's like 4 people in their squad. Omori is the current leader here, and if we play the video, you can kind of see that this animation pops up, and there's like a spiral that happens. You see that spiral? I think the spiral just looks so much cooler rather than what I got going on here. If I hold tab, it just comes out from the center like that. I just think the spiral looks so much cooler. My goal now is to try and not only implement the spiral, but show you guys how you can go about doing it yourself and how to just in general approach a game dev problem. So yeah, without further ado. Alright, so I drew this diagram where on the left we have our current animation and on the right we have the animation that we want to get to. So on the one on the left, we start from this middle point. We'll call it the origin. This is where the player currently is, and it's at 0, 0. And if we're going to the right, that's at 1, 0, where x is 1 and y is 0. On the bottom, we have 0, -1. On the left, we have -1, 0. And on the top, we have 0, 1. If you look on the right, we actually still have the same thing, where we start at a 0, 0, and we end up at the same places. We end up with 1, 0 for the right, 0, -1 for the bottom, -1, 0 for the left, and 0, 1 for the top. Now, to be able to actually solve an animation problem, we first need to know what animation even is. Now, animation can have many definitions out there, but I'm going to use this one because this is how I understand animation. So to me, animation is position in time. Position, we've already seen a couple here, 0, 0, 1, 0, etc. Position is where we are at any point. It's our x and y given time. Now, time is actually what defines the movement. It's what creates the movement and changes the x and y to go from 0, 0 to 1, 0 if we're going right. We can assign this to be t. Mathematically, we can kind of think of this as a function, where if we have time, we can know the position of where something should be at any point. In math, we often talk about things like f of x or g of x or h of t or h of x. It doesn't really matter, right? Here, we'll define it as animation of t. And this should give us our x and y. Now, the thing is, our animation specifically has a definitive start and a definitive end. Some animations, they can be idle where they go on forever, but ours is specifically get from one place to the next place. We also have to define a constraint here of how long this animation lasts. We can say that t is all values within 0 to some duration. For ease of mind, maybe you can think of duration as 1 second. I think that's what I'll do for my game, but this could be any value. It just helps us keep it a little bit more dynamic if we wanted to change the duration in the future. Yeah, if we think of animation as a function, we can start from the center and go out to our target within the duration period. Now let's break down the first example a little bit more, starting from that origin, going to the right. We know that the origin is still at 0, 0, and that the right is still 1, 0. And given time, we should be able to slowly make our way over from 0, 0 to 1, 0. One thing to note is that time is continuous. Time increases pretty smoothly from 0 to duration. So our animation should look pretty smooth going from 0, 0 to 1, 0. Let's say that duration is 1 second. If the duration is 1 second, if t is half a second, it should be somewhere in the middle. It should be somewhere like right here. If t is equal to 0.5, given our duration is 1 second, that should imply that our positions would actually be 0.5 for x and still 0 for y. This makes sense because 0.5 is in the middle of 0 to 1, and 0.5 for t is in the middle for 0 to duration. The concept I've just demonstrated to you is known as linear interpolation. This is a concept in math where given any 2 points, in this case our origin at 0, 0, and where we're trying to get to 1, 0, our second point, given 2 points, we can derive any point on the line in between those 2 points, as long as we have some parameter to tell us where on the line we should be. In this case, t is what determines where on the line we should be. Thinking about it more in terms of mathematical functions, a mathematical function has one input and spits out an output. Here we have t, which is one input, but it's spitting out x and y, which are 2 outputs. So we should probably break it down into 2 separate equations, where our first function is line x of t, and this spits out an x, and line y of t, and this will spit out a y. We can use linear interpolation and apply it to both the line x of t and line y of t functions. A linear interpolation equation in the textbooks usually looks like this. Let's break it down a little bit. So where are our 2 points? Our first point is x1, y1, and our second is x2, y2. You can kind of see them labeled here, and that means that our x here is our input, and our y is the output. Now the equation is a little bit confusing in that it's in terms of x's and y's, because x's and y's are usually used for our points, but based on our functions here, we're actually in terms of t. So rather than thinking of x as positions, all the x's are actually in terms of t, and y is in terms of the position for either x or y. We have 2 different functions here, but they will use the same equation. They'll just provide different variables given on what the position targets are. T will still be the same. It's just the positions that will change. So let's apply this to line x. Remember, we're trying to go from 0, 0 to 1, 0. For line x, we stumble upon our first thing, y1. What is that? Remember, y's are in terms of the position. So it's the position that we're trying to either come from or get to. y1, that's where we're starting from. The starting position for x is right here, minus 0. Now what's y2? Well, y2 is right here actually. This is our target position that we're trying to get to. This is the second point. So we have 1 for y2 minus y1, we put already here, 0. And it's over x2 minus x1. What is that? We know that x's are in terms of t. So we need to figure out what x2 and x1 are in terms of t. If we scroll above, we actually already defined that t is increasing from 0 to duration. So we can view duration actually as our target x2, and 0 is our starting x1. Here we can put duration minus 0, where duration is how long it should take, and 0 is when the animation started, which is at 0 seconds. Now we have our input here, x. Remember, x is the input and y is the output. If line x of t is our output, that must mean that t is our input. Now again, what is x1? Well, x1 is where t starts. That would just be 0. And we can simplify this equation a little bit more. There's a lot of zeros in here, right? So let's just clean up the equation a little bit. We can go ahead and do the same thing for line y. Because it's in terms of t, it's still going to be duration minus 0. It's t minus 0. Line y of t is actually just going to be 0 times t. Now, the reason I bring up this example is because we can get a little bit of intuition behind it, right? If you look at it, 0t makes sense. When we multiply by 0, we always get 0. And if you think about it, we started at 0 for y, and we still ended up at 0 for y. So y should have always been at 0 the entire time. It's a flat line. It is parallel to the horizontal axis. You can see that it goes from 0, 0 to 1, 0. The y actually never changes here. And for this equation, that works really well. So that is linear interpolation. That is the first part that gets us this problem right here. To do the same thing for all the other ones, we just need to interpolate and plug and chug the target positions for the other targets. The one on the bottom, we would plug in 0 and -1 for the y2s. The one on the left, we plug in -1 and 0 for the y2s. And the one on top, we plug in 0 and 1 for the y2s, where 0, 0 in the middle is still the y1s. Now, if we look on the right here, we actually can still see a similar behavior occurring. We start at the origin, 0, 0, and we expand outwards to any of those positions. Linear interpolation in this case creates kind of this growing feeling from going from the origin out to some pre-designated spot. On the right here, we still have that expansion happening over time, where we start from the origin and we end up at one of these targets. We can still use the concept of linear interpolation here. The only difference is that now there's this circular motion that's happening at the same time as the expansion. And if you notice here, we actually go around the circle once. Other than linear interpolation, there's another mathematical function we can use to create that circular motion. If y'all are familiar with algebra, there is this other concept known as the unit circle. So the unit circle is a way to derive any point on the circle from the origin. Remember, our origin is still 0, 0. We can derive any point on this circle given some input parameter. The reason it's called a unit circle is because it is always 1 away from the origin. The radius from the origin to any point on the circle is 1 away. And this works really well with our example because our drawings here show that we are going from the origin to 1 away. The target is always going to be 1 away. Our unit circle really helps out with determining this point. Now, the unit circle equation is usually denoted as such: cosine theta, sine theta. What cosine theta is representing is our x, and sine theta is representing our y. What is theta? Well, theta is a value that is inclusive between 0 and 2 pi. If theta is 0, we actually end up at this value right here, which is 1, 0. And then if we increase theta to be half pi, we actually get this point right here. And this point is at 0, 1. As theta increases, we get -1, 0. This would be pi. And then we increase a little bit more, and now theta is equivalent to 3/2 pi. And this evaluates to the position 0, -1. And we make our way back up here, and we end up at 2 pi. Or 0. That's why theta goes from 0 to 2 pi, because it includes all values 0 to 2 pi to make the full circle. If we increase theta, and we get this circular motion, that's kind of what we want for the spiral animation. If we change theta, what should we change it to? Well, similar to linear interpolation, time is our function to create the animation. we actually need to make things in terms of t. So we need to map our time, which is 0 to duration, to this. And only then will we go around the unit circle in the duration that we're specifying. It's called a unit circle because it's one away. So let's go ahead and write the mathematical functions for this. Let's call it circle x of t. And this is equal to this cos theta. And we also have a circle y of t, which is equal to sine theta. Now the thing is, we want to still write things in terms of t and not theta, right? How do we go from theta to t? If you've ever taken chemistry and learned about this thing called stoichiometry, the idea is that we can convert between units within different spaces. T is in terms of time, which is like seconds or minutes, and theta is in terms of radians. To use t properly, we actually need to take t and convert it into the proper space, which is the theta space. First, what we do is we divide by duration, and then we multiply by 2 pi. Now, the reason we do this, let's think about it inherently, right? What does dividing by duration do? If duration is our max length, we are dividing t by duration. We're getting kind of a percentage or a fraction of t relative to its duration. And then when we multiply it by 2 pi, we're taking the fraction of 2 pi and mapping it into the space for 0 to 2 pi. That's how we are able to go from one space to the next space. Oh, missed this d. We can rewrite these equations so that it becomes cosine of 2 pi t over duration. And we can do the same thing on the bottom, sine of 2 pi t over duration. And there we go. We have our unit circle and we have our linear interpolation. Now, how do we actually combine these two together so that it makes sense for the spiral animation? If we look at it, as time is passing, we're making the circular motion as we're expanding outwards. So how does linear interpolation and unit circles do that? Well, the unit circle goes around the circle as such, and linear interpolation allows us to expand from the origin, making the spiral animation together. If we take a look back at our linear interpolation requires 2 points here. These are the targets. Now, in our previous implementation, the targets were pre-designated. They were already defined to be 1, 0, 0, negative 1, negative 1, 0, and 0, 1. But what if these targets are moving around the circle? If it moves around the circle, that means we get an expansion where we not only go outward, but we also go circularly outward. I'll draw another circle here. If we start in the middle, t is 0, we're actually still in the middle, right? We start in the middle and we expand outwards until we get to our final destination. If t increases, we are growing, but we're also moving because of the unit circle. So let's say we're 1/4 of the duration. If the duration is 1 second, we're at 0.25 seconds. We should be around right here. Why? Because the unit circle actually made us move this way in 0.25 seconds, and it's saying that this is where we should be at. This is roughly 1/4 away from that point, and you can see we kind of went like that, right? This is 0.25 seconds. If we're at 1/2 second, we should be somewhere in the middle right here. So you can kind of see we made a bit more of a spiral. And then once we're at 0.75 seconds, we're at this bottom one over here. We actually end up a little closer to the outside until we eventually get to that point here, which is at 1 second. The two work together to create the spiral animation. One thing you may have noticed is that the unit circle is actually going to be the one to define the target position that will be used for the linear interpolation. unit circle defines target, and linear interpolation expands to target. Now, there's a couple more things we can do to mess with these equations to make it look cooler and all that, but that is the general concept of how you would go about deriving a simple spiral animation from the original linear interpolation. Okay, now that we've figured out pretty much all of the maths behind it, we can go on and get to the fun part, which is the coding. So currently, like I said before, we already have the linear interpolation part. This might look a little different than what we've been talking about before, but I'll break it down to you what each thing means. So scalar, this is actually our t that we've been talking about within our equations, where t goes from 0 to duration. A little nuance about my code is that I divide scalar by duration. And what does that do? It basically takes t, which is mapping from 0 to duration. If we divide t by duration, I'll just call it dir. This actually means that this will include all values from 0 to 1. We're using it kind of like a scalar, where we're going from 0 to 1, where 0 is the beginning of the animation and 1 is the end of our animation. So that's what scalar is doing. And then squad pause, this is the exact same thing as here, where it's 0, 1, 1, 0, 0, negative 1, negative 1, 0. It's just defining the predefined coordinates that we've had beforehand. And you can see this is squad pause. And for size of 4, we have 4 members in our squad. I define it to be 0, 1, 1, 0, 0, negative 1, and negative 1, 0, respective to their directions. Now, there's this last variable that I didn't mention before, but it actually is quite important. It's called UI spacing. And if we don't have UI spacing, like if we just multiply by 1, 1 is identity multiplication, right? If we just have 1, watch what happens in the animation itself. You see that? We basically just move 1 pixel away. And that's because the coordinates that we've been defining are just 1 unit. And in my game, a unit is a pixel. To create a more dramatic effect and a clearer image, we actually need to multiply by some spacing to make it look a little bit better and more readable. In my game, I have this spacing variable to create that spacing. Now remember that what we've talked about before is that the unit circle will actually be the one to dynamically define the target position for the linear interpolation. The unit circle here will define where the interpolation should go to. Well, the beauty of the unit circle is that the unit circle is always 1 away from the origin. If we wanted it to be further away, all we would actually have to do is multiply some spacing by the respective functions. And that way we can get a distance that's further than just 1 unit away. So without further ado, let's get started with this code. So first, I'm gonna just outline the steps here. So first is the unit circle to derive the target pause. And then we also have the linear interpolation to derive the final local position. Now, the thing here, this final step, this might be different for all of you, but basically for my game, this just converts it into screen space / world space from the local origin that we've been using at 0, 0. Let's do the unit circle part first. If we look back at our equation for the unit circle, we can see that we have cosine and sine for our x and y's. And remember, we're in theta, which is radians, and we need to convert it to time. Here, I do t divided by duration. But remember, in my game, I already take t and I divide it by duration, so we don't need to do that anymore. We can just say t times 2 pi, or in this case, scalar times 2 pi. So our new radians actually is going to be that scalar times 2 times music functions pi. I already have a predefined library, but yeah, use whatever value you need to, but just know that pi is representing 3.141592653589792, and on and on. Now, if we then use our functions here, we can say that circle x is equal to cosine of radians, and that circle y is sine of radians. Now we can plug this into our final equation here for the final calculations. You can see that we will go in a circle. Okay, you might not be able to see it, but remember the reason why. It's only going a pixel apart. So we actually need to still multiply these values by the UI spacing. When we run the code, you'll now see that the circle goes all the way around the player as such. See that? Okay, now let's also do the linear interpolation. So I'll call it line x, because remember from here we defined it as line x and line y. In terms of the equation here, we know that y1, or that the y's are in terms of position. And we know that the x's are in terms of time. Well, time always starts at 0, so we never need this x1, right? That's why it becomes t minus 0 here. And when we simplify the equation at the very bottom here, line xt is equal to 1 over duration times t. This 1 actually represents the y2. That's the position that we're trying to get to over here. We're trying to go from 0 to 1. This value is going to be the target position that came from the unit circle equation. And because t is already divided by duration, we can just say 1 times t. So here, we want to take the target position, which in this case is circle x, and multiply it by the scalar. And the scalar is what will cause that growing motion, remember? Similarly with line y, we can multiply circle y by the scalar. And now, when we change this and input the values, we should be able to actually see the spiral starting to come together. See that? So now we start at the origin and we grow out, we expand out, and we end up making the full circular motion to where we're trying to go to, which is over here. Now you may be wondering, weren't there 4 players, or weren't there 4 characters here? And yeah, that's right, there are 4 characters. But the thing is, because of the way we've written the code, we've only done the calculations for one of the characters. We actually ended up drawing all of the characters on top of each other, and that's why you're kind of seeing only one. So what we need to do now is we need to create some spacing to be able to draw them offset from each other by a certain amount. Well, how much do we offset it by? We know that the total duration it takes to go around the circle is from 0 to 2 pi. So it takes 2 pi to get around this entire circle. So if we take 2 pi and divide it by the total number of people within the squad, we should get some pretty even spacing. I'll go ahead and create some offset here. And I'll use I because I increments over time. And I'll multiply it by 2 pi divided by the squad size. So what is this doing? Basically, what is happening is per character, that's what I is, the I defines each character. Per character, we are going to move, in this case, squad is 4, a fourth of the circle. That way, we can have them always be a fourth apart from each other. If you look at the initial diagram, they're always a fourth apart from each other, and even in the spiral diagram, they're a fourth apart from each other. We're basically saying take the whole circle and cut it into fourths, and each person will get a fourth of that entire circle. That way we can individually see all of them. So if we add this to our current radians, we should be able to see each individual person. Like that. Now that is looking like the Omori animation. Now there's a couple more things here that I want to do to clean it up. If you notice, the leader used to be on the top, the crown used to be on the top here, but now the leader is on the right. And that's because the unit circle starts on the right and goes around counterclockwise until it gets back to the right. Well, what I want to do is actually I want it to be on the top. I want the leader to be on the top, and I want it to go clockwise instead of counterclockwise. So how do we go about doing that? Well, in this equation here, we know that radians is time passing, or it's derived from time passing. The scalar is what causes the time to pass. The thing is, in a unit circle, if you supply values going the other way, we actually get the inverse, and the circle will go the other way. So if we negate time, we'll be able to go the other direction for the unit circle. So here we can negate time to make it go clockwise instead. Remember to surround everything within it. And the last thing is we need to make sure that instead of starting on the right, the leader should be on the top, right? Correct. The leader is currently here on the right, but we need the leader to be here on the top. So how do we get from here to here? Well, we know the entire duration is 2 pi. That means we go 0, half pi, pi, 3/2 pi, 2 pi. So we just need to add half pi to our radians to shift the radians over to the top. And that should be what is needed to get our leader to the top. Now let's take a look at that. Oh, I see. Because we are going the other way, we actually need to, instead of adding half pi, we need to subtract half pi. And now the leader is on the top. And notice how everything is assigned correctly. We have W up here, A is on the left, S is down here, and D is on the right. And that is how we get a clockwise spiral animation from a linear interpolation. But yeah, hopefully you guys found that pretty entertaining or educationally valuable. And hopefully you guys learned a thing or two about this and enjoyed the mathematical breakdowns behind it. But yeah, that's how you make a spiral animation, and just in general, that's how you break down a problem to make sure that like everything's mathematically sound. I'll also show a couple of demonstrations as well